Hello everyone, welcome to the first of 4 videos covering examples from Chapter 9. In this video we're going to go over an example of a simple ANOVA model. So the full example is on screen here, but in summary we have a researcher who's interested in testing out 3 different drugs. The drugs are used to resolve headaches. He has 15 participants and divides them into 3 groups for drugs A, B, and C. The researcher then measured the time it takes for the headaches to resolve after the administering of the 3 different drugs, and the values are reported in the table on screen. So our question of interest is to determine whether the true mean times to relief under the 3 different drugs are equal, or if at least one of the means differs significantly. So let's begin, jump right over to SAS. So unlike some of the other programs we've written so far in SAS, we're not going to start right away with the dataset. We're going to start with this options command. So options, PS equals 62. This stands for page size equals 62, which limits our number of lines on the output to 62 lines, and LS, which is line size, which limits the number of characters per line. And in this case, we're just going to limit the line size to 80 characters. And the purpose of this line is just to make the output just a bit more user-friendly. So our next couple of lines are just to import the data, so call the data function, and then make sure to import our variables, and make sure that treatment is a categorical variable. Call the data lines function, then paste in our data, and close it out with a run function. Then we can go ahead and run that, make sure that the data is importing correctly. So everything looks like it imported correctly, so we can head back over to the code tab and continue with our analysis. So we can start off the analysis using some summary statistics. So we can call the procmeans function, use variable time to specify the response variable, then class treatment to specify the grouping variable. Then we can close that with a run statement. So we can go ahead and run this procmeans function for the summary statistics. So looking at the means here, we can see that group A and B seem relatively similar, and even B and C seem relatively similar. However, comparing group A and C, we see that there's a 13-minute difference between the mean times. So that might lead us to believe that there is a significant difference. However, obviously we're going to need some more formalized testing in the ANOVA analysis to rightfully compare the 3. So if we want some more detailed summary statistics, we can use the proc univariate with code that's very similar to the procmeans. However, we're going to use that plots option in that first line to specify that we want the distribution and QQ plots printed with our output. So if we go ahead and run this univariate function, it's going to give us some more detailed statistics compared to the means function, but this time it's going to be broken out by the different treatments. So right now we're looking at the summary statistics for treatment A. And then if we scroll down a bit farther, we can see the QQ plot for treatment A. Everything looks pretty linear. We can assume normality. Then if we scroll down to treatment B, again, we can see all the summary statistics. Scrolling down, we can see the distribution plot for treatment B, and then scrolling down a bit more, we can see the QQ plot for treatment B, and again, looks pretty linear. We can assume normality. And then finally, treatment C, you can see all the summary statistics here, and then scrolling down towards the plots, we can see the distribution plot and the QQ plot, and again, looks pretty linear. And then finally, we can jump back over to the code section and begin the final function for our ANOVA analysis. So starting off, we're going to use proc ANOVA and then specify our data. We're going to use class treatment to define the grouping variable. We're then going to use model time equals treatment to define time as our outcome and treatment as our grouping variable. This line here tells SAS that we want to run a Levin's test to check for homogeneity of variances. So these next couple of lines of code here are used for the multiple comparison procedures. These comparisons are useful for a more granular analysis, allowing for a one-to-one comparison between groups. And as you can see, the code in which you make these comparisons are all pretty similar. So they all start with means, followed by the grouping variable and a /, then the comparison method, concluding with CLDIF, The options for the different comparison methods are as follows. Use T for Fisher's LSD. Use Bon for the Bonferroni adjustment. Use Sheffey for the Sheffey procedure. Finally, use option Tukey for the Tukey's procedure. And with that concluded, we're ready to actually run the final analysis. So if we go ahead and highlight and run. All right, and so this first section we see here is just a description of our data, so the different levels of treatment as well as the number of observations. And this second part here is arguably the most important. So in these tables, there's some really critical values, the first of which is the mean square error. So in this case, the mean square error is estimated to be 20.833, and this is the estimate of the common population variance. The next important value here is the R-square value. This is the variation in the data that is associated with the treatment. And then one last metric before the analysis is the RMSE. In this case, it's 4.56. This is just the estimate of the common population standard deviation, or the square root of the mean square error. With all that said, we can move on to the final analysis. And so the third table here, we can see the source, the degrees of freedom, the ANOVA sum of squares, the mean square, the f-value, and the p-value here. This p-value is associated with our question of interest, being whether or not the means of all the groups are equal. So here you can see that the p-value is below 0.05, so we have enough evidence to reject the null hypothesis, and we can conclude that at least one pair of means is not equal between the three treatments. However, in order for this analysis to hold true, we have to meet certain conditions of the ANOVA procedure. The first of which is normality of the errors, which we checked with the QQ plots where everything looked linear and relatively normal. And the next assumption is the homogeneity of the variances between the groups. And this can be checked using the Levin's test. Here, the null hypothesis is that the variances are equal, and the alternative is that the null hypothesis is false. And thus, you can see here that the p-value is rather large at 0.37, well above our cutoff of 0.05. We don't have enough evidence to reject the null hypothesis, and we can conclude that the variances are in fact equal. And as a result, the analysis that we made earlier still holds true. Natural continuation of the question, however, is figuring out which of the means actually differ. And so this leads us to the different comparison methods. So as we scroll down, we'll see the different comparison methods that we had called for using the function earlier. And using those, we can analyze and determine which of the one-on-one comparisons actually differ. So the first comparison method we see is the Fisher method. This is the most liberal and often has the most narrow confidence intervals. So you can see here that the significant comparisons are denoted with the 3 stars. So as you can see, according to the Fisher's methodology, there's only 2 groups that share a similar mean, being groups B and C, and the others differ significantly. Moving on to Bonferroni's methodology, we will be able to see that there's only 2 groups that differ significantly, and those groups being A and C. And then as we scroll down here, we'll see that both the Sheffey and Tukey methodology will share similar results to the Bonferroni method. And all 3 of the final methodologies claim that the only significant difference lies with the comparison between groups A and C. So this concludes the analysis for this example, but we're going to continue ANOVA analysis in the next 3 videos as well. Thank you very much for watching.